Hello and welcome to the very last day of Advent of Code, day 25. And I felt that the puzzle was pretty hard to read, but the actual, code and solution wasn't so bad. So anyway, let's jump into that and solve it. Okay, so the input for our puzzle today is 2 public keys for a card and a door. And the problem goes into a lot more details about the card and the door, but it's mostly extraneous information for what we need to solve. And so this is the sample input. It doesn't matter which one is the card in the door due to the way the algorithm works out. So you could treat either of them as the card or the door. And the first step of what we need to do is figure out the secret loop size for each of these 2 public keys. So we're actually implementing like a thing that looks very similar to some public key cryptography. Usually the secrets are secret and, there isn't a way to determine them, but for this we're, breaking that in a way. The loop size is determined by the number of times that it takes to do the following loop. So you start with the number 1, and each loop you multiply by 7, and this is kind of a hard-coded number, and that's fine. And then we get the remainder of a division by this prime number 20, 20, 12, 27, which is in 2 days for me. But the number of times that it takes to get this loop size is the loop size for that key. And so each of these 2 keys have their own loop size. Now, based on the actual problem description, we don't have to compute the loop size for both of them. However, one of these is 8 and the other one is 11, and we'll actually show that as I do the problem. And the next part of the problem is to find the shared encryption key. The shared encryption key uses the same algorithm, but instead of multiplying by 7, it multiplies by the other key, and it runs it the number of loop sizes of the opposite key. So if you're, computing this one against this one, you would use this as the multiplier and the loop size of this one as the other part. And again, it's the same, remainder division here. And that actually works both ways due to the way that these 2 numbers are set up. But let's jump into that. So I made a function called Git Loop Size, which takes an integer and returns an integer. Oh, I guess before we even do that, let's do the parsing. So parsing for this is pretty easy. It's just 2 integers, and so I did, card and door equals int part for part in s.split. That way we just get the integer parts out. So print card door. And if we run this part1.py, you'll see that we get those 2 numbers here. All right, so get loop size. So we start at 1 and we multiply by 7. So that says that current equals 1, and then I equals 0. So we're going to count the number of times we run this loop. And then while current does not equal n, so we're going to loop until n is equal to, current is equal to this number here based on this modulo. And then we need to multiply by 7, so we'll do current times equals 7, and then we need to get the remainder of division by this, and so we can do current mod equals this. Current, and every loop we need to increment I because we ran that number of times, and then finally we return I, and so this will be our get loop size. So now if we were to do print get loop size card and do the same thing for door, we should get 8 and 11. Yep, and we get 8. So the loop size of the card is 8 and the loop size of the door is 11. So that's part 1, or I guess the first part of part 1. And then the second part is determine the shared encryption key. So I did a second function for that. So get encryption key, and that takes key 1, which is an int, and then loop size 2, which is an int. That way we get the key from one and the loop size from the other, just as a hint there. And this will return an int. And so again, we run that same sort of algorithm. So n equals 1, and then for this in range loop size 2, so run it loop size number of times, multiply by the key, so we'll do n times equals key 1, and then n mod equals 20, 20, 12, 27, and then finally we return n. So that's the encryption key algorithm. And it turns out you don't really care which way you do this. So if you do, print get encryption key with card and get loop size door, door, 1, 2, 3. You can also flip these. So if you did card and door, it works either way. So that's just part of how this algorithm works. And that is the value we expect. So I'm actually just going to change this print to a return, and that gets us our answer. Now, this is kind of the brute force approach to this. It turns out that the brute force is fast enough to solve this for the actual puzzle input, but there is a smarter algorithm for this that I don't understand, so I'm not going to show it to you, but it has to do with, picking an upper and lower bound, if I recall correctly. The fast algorithm runs in square root n of time, which I'm not super familiar with any algorithms that end up in that time, but that's how you can figure that out. But anyway, this is, kind of a very straightforward, simple solution to this. It's not very fast because, the loop size can be very large for this, and so it actually runs for a lot of work for the real input. For these ones, it's 8 and 11, so it's, trivial work, essentially. But yeah, this is how to implement part 2. And for part 1 and part 2, I'm gonna leave that one up to you, as to not spoil it. But part 2 is a pretty fun one. But anyway, that's day 25. Hopefully you had a fun time following Advent of Code. I had a blast doing all these problems, so they were really fun for me. But anyway, I guess I'll see you next year. Have a good one. Bye.